Well, welcome again to our journey into algebra and number theory, and we've been looking in this whole section at the structure of these U sub m groups. And we're going to jump back now from the algebra back to number theory and see what interesting information our structure theorems give us about the number theoretic aspects. So we recall that the size of this group is 5m. So 5m is the number of integers less or equal to m and relatively prime to m. And we'd like to know a little bit more about this Euler's phi function, as it's called. It itself is a fascinating object. So immediately, as a result of our structure theorems, we can say that if I take an integer n and factor it as a times b, where a and b are relatively prime, then I can factorise this U group as U sub A direct product U sub B. And these two groups are isomorphic, and that means the number of elements in U sub n is the number of elements in this, and this is just a set of ordered pairs, so this is the number of elements in U sub A times the number of elements in U sub B, and immediately we have this beautiful result here that phi is multiplicative. And that comes directly out of the algebra, looking at the algebraic structure of U sub n. So phi of n is 5a times phi of b. So we say that phi is a multiplicative function. Now this simple idea now generalizes to give us the following theorem. So if we take the prime decomposition of n into its prime factors in the usual way, then phi of n is just phi of each of these factors here. So phi of p1 to the alpha 1 and so on. So what we'd like then is a nice simple formula for phi of p to the alpha. If we know what phi does to a power of prime, then from this we can work out what phi does to anything. So we're going to do this by a simple counting argument. So I'm going to write down all the numbers from 1 up to p to the alpha minus 1. There are that many of these, and in the process of doing that we start writing 1, 2, 3 and so on. Eventually we'll come to p, then we'll come to a 2p and a 3p all the way up to p to the alpha minus 1 times p, and that'll be the last multiple of p in here. And we now look through this list and we simply write down the elements in this set that are not relatively prime to p to the alpha, and they're clearly going to be the p, the 2p and so on. So there is a list of the numbers in this set that are not relatively prime to p to the alpha. There are that many of them, and so phi of p to the alpha then is the number of elements in the whole set, which was p to the alpha minus 1, subtract the number of elements that were not relatively prime to p to the alpha, and behold, there's our formula, which we can also write, and some people do interestingly, as p to the alpha times 1 minus 1 over p. Now we can use the formula now to evaluate phi of n for any integer n. So phi of 30, we just take 30 and prime factorise it. Now if you put alpha to be 1 in here, then phi of p of course is just p minus 1, as common sense would tell you anyway. So phi of 2 is 1, phi of 3 is 2, phi of 5 is 4, multiply these you get 8. 100 I can factorise as 2 squared be 5 squared, and again using our formula this is 2 squared minus 2, 5 squared minus 5, so that's 2 times 20, which is 40. So that means of course there are 40 numbers between 1 and 100 that are relatively prime to 100. Now we can use this to do some other problems as well, which I've done on a separate sheet here just to put a bit more detail in. So we'd like to work out, for example, 47 to the 813 modulo 60. This of course is a ginormous number, and we want to know what's the remainder when you take this ginormous number and divide it by 60. And of course we're going to recall Euler's formula that we've had before, and that is that if a and n are relatively prime, then a to the phi of n is congruent to 1 mod n. This was this lovely generalization of Fermat's little theorem. So in our example here, 47 to the 560 is 1 mod 60, and I'm going to work out 560. Now 560 is, the 60 is 5 times 4 times 3. So that's 5 is 4, this is 2 squared minus 2 times 2 is 16. So 560 is 16. So plugging that back into here, we have 47 then to the 16 is 1 modulo 60. That is, whenever we see a factor of 47 to the 16, we can just replace it with 1. So the key then to work out this number up here is to see what 813 is modulo 16. Well, a little bit of simple arithmetic shows you that 813 is just 13 mod 16, in fact. You can see that because 16 times 50 is 800, I think, so that'll give me the 13 there. And that means 47 to the 813 is just the same as 47 to the 13 mod 60. And we've still got to calculate this beast here, so again by hand I just checked, I started calculating the powers of 47, so I worked out 47 squared, and then square it again, you get 47 to the 4 turns out to be 1 modulo 60. So again, that means whenever you see 47 to the 4 in here, it's just replace it with a 1. And this number here is 1 then modulo 4, so 47 to the 13 is just 47 to the 1 modulo 60. Second example is to find the number of distinct fractions less than 1 with a denominator less than 100. So if I were to write down all the fractions that are distinct, all positive fractions less than 1, then with the denominator less than 100, so that means I want there are fractions of this shape, I want A and B to be relatively prime. A's got to be bigger or equal to 1, strictly less than B, and B's got to be less or equal to 100. So all we need to do then is to find the number of numbers less or equal to 100 that are relatively prime to 100, and there are 40 of those because we've seen before 500 is equal to 40. This Euler's phi function has a lot of very, very interesting properties, which we'll be having a look at. Well, you'll see in lots of other number theory books the properties of Euler's phi function. It's extremely important in analytic number theory and in number theory generally, is Euler's phi function. However, at the moment we want to return back to algebra, and I'm then just going to then summarize what the story is so far before we do that. So I'm going to compare the structures here of what we've seen to summarize everything. So firstly, we looked at z sub n under addition, this group of integers modulo n under addition. We saw this is always cyclic. We saw that if A and B are relatively prime, then ZAB is isomorphic to the direct sum of ZA and ZB. And we saw how that connected with the Chinese remainder theorem. And the number of elements in this set, of course, is n. On the other hand, the U groups, the ones that are numbers that are relatively prime to n, this forms a group under multiplication. It's not necessarily cyclic. We'll come to that question in a moment. But once again, we have an analogue of this, that if A and B are relatively prime, then the U group AB is isomorphic to the direct product of UA and UB. And also, the number of elements in this set is 5n. Now, the question then is, we've seen that this is not necessarily cyclic. Sometimes it is, sometimes it's not. Well, we want to know, how do we tell when this group is cyclic? Now, a partial answer, not the full story, which I'll give you later, partial answer turns out to be when n is prime, and I'm going to give you the full story later, but in order to prove just this little bit, the proof of this is fairly difficult, and in fact requires a number of technical lemmas or lemmata, if you will, and we'll have a look at that in the next video.